Welcome back. What you see in front of you is a pressure versus volume graph for an ideal gas as it undergoes a series of thermodynamic processes. And we follow the graph clockwise as it goes from A to B, B to C, and C back to A. And what we want to do is, as we talk about the graph, we want to relate it back to our first law. And the first law of thermodynamics looks as follows. The internal energy of the gas, or the change in internal energy of the gas, is written as delta U. And the things that affect the internal energy of the gas are any work done on the gas by expanding or contracting the cylinder itself, or the volume. In other words, squeezing the gas or expanding the gas. Or we can add and remove heat. And obviously if we add and remove heat directly, we'll change the internal energy of the gas. Now just a couple of things to remember as we're going through this process. The internal energy of the gas is related to the temperature. So at any given point, the internal energy of the gas is given by this formula. 3/2 times the number of molecules times Boltzmann's constant times temperature. But really what we need to understand is that this internal energy is related to the absolute temperature in Kelvin of the gas itself. So if the internal energy changes, then the temperature must change. The change in internal energy is proportional to the change in temperature. The other thing we have to remember is that all ideal gases, including the one represented on this cycle, have to adhere to the ideal gas law, which is simply PV is nRT, or nKT, depending on how you want to write it. So all of these things are true as we move around in that cycle. Now we want to keep track and keep organized as to what's happening to delta U, Q, and W as the gas moves around. So to do this, let's make a table. We'll construct a table that's got delta U, Q, and W on the rows, and on the columns we'll look at the processes, and then we'll just simply assign whether or not they're positive or negative as we go through it. So it'll look like this. Okay, so we've constructed our table. Now let's see if we can identify some of these processes. If you look at the graph from C to A, we see that the pressure remains at 2 kilopascals. So as the gas is squeezing from 10 meters cubed of volume down to 6 meters cubed of volume, so the gas is basically getting squeezed into a smaller space, the pressure remains constant. And if the pressure doesn't change, we call that isobaric. So C to A is an isobaric process. Now the other obvious one is the vertical line from B to C. From B to C, the pressure drops from 8 kilopascals down to 2, but the volume remains at 10 meters cubed. So the gas is remaining with its original volume while the pressure decreases. So if the volume doesn't change, we call that isochoric or isovolumetric. So B to C is isochoric. Now if you'll recall from the other processes, A to B is neither isothermal nor adiabatic just based on its shape. Isothermal represents an inverse relationship between P and V since the temperature remains constant, and you can actually see that from your equation PV equals nRT. If it was isothermal, the entire right-hand side of this equation would be constant. So pressure times volume is a constant, or pressure is inversely related to volume, and we showed you that in the tutorial. So that gives you an inverse shape of a graph. Also, if temperature was constant, that means the entire right-hand side is constant, which means P times V is constant. So in order to be isothermal, pressure times volume has to give you the same value at any point on that isotherm. And you see at point A, pressure times volume is 2 times 6. We won't worry about the units for now. But we've got 12 at A and 8 times 10 at B, which is 80. So clearly PV is not constant, therefore that's not an isotherm. And then the other process is adiabatic, when no heat is added or removed. And adiabatic looks very similar to an isothermal process, but it drops a little bit in temperature as it expands. So A to B is some unknown process, but clearly the gas is expanding, the volume is getting bigger, and the pressure is getting bigger. So now let's go and see if we can identify the signs of each of these things. Let's start with delta U from A to B. Remember, delta U, or change in internal energy, is directly related to change in temperature. So if delta U changes, the temperature must be changing, or vice versa. If we find a change in temperature, then we must have a change in internal energy. Now, also we know that the temperature is related to PV. We just mentioned that. So if I check pressure times volume at A and pressure times volume at B, if PV increases, then the temperature is increasing, which means delta U is on the increase. So if we quickly work it out as I just did before, we see that PV at A, and I'll just do it right on the graph, at location A, PV is 2 kilopascals, so 2,000 pascals, and my volume is 6 meters cubed. Pascals and meters cubed go together. And when I do that, I end up getting 12,000 Pascal meters cubed, which we know as the joule. So that's my internal energy at location A. At location B, if I do the same thing, I get PV at B to equal 8,000 times 10. So it becomes 80,000 joules. So clearly my PV value is going from 12,000 joules to 80,000 joules, so it's increasing. So delta U from A to B is positive, and that's because it goes from 12,000 to 80,000. Now I'm going to remove some of the clutter from my graph and just leave my values of PV that I calculated at A and B. Let's use our FET simulation to emulate what happens when the gas expands from A to B and the pressure increases as well. So our FET sim, we'll use the same one that we used previously. So I've got this empty chamber. I'll pump some gas into it. We'll let it reach a little bit of equilibrium as the gas molecules start to randomly be distributed throughout the chamber. Now from A to B, if I just go back here, the gas is expanding. So I'm increasing my volume. So I'm going to make my little guy, pull on that chamber to the left to increase the volume. Now watch what happens to the pressure. It won't be anything shocking, but watch what happens. If I expand the gas, the molecules now have more freedom to move around, and they'll make less collisions with the wall. So you'll see that as I expand the gas, the pressure actually drops. So our pressure drops to 0.5. Now, how do I keep the pressure up? Well, I would have to add heat. If I want the pressure to go up like the graph is telling us to, heat would have to be added so that the pressure and the temperature are increasing, as predicted by the graph itself. So we've now figured out that Q in that process is also positive, just by using some logic. Let's go back to our table and fill this in. So Q from A to B is positive as well, adding heat. Now what about from B to C? From B to C, the volume of that gas does not change. So if the volume of the gas is not changing, then I can't be doing any work. The little man in the simulation that we keep looking at is either squeezing the gas or the gas is pushing on him. And we call that work. If he applies a force over a distance, or if the gas applies a force over a distance acting on him, then work is done. So clearly if the volume does not change, then work done in that section has to be 0. So we'll fill that in as well. So the work done from B to C is 0. Now what about the work done from A to B? We haven't filled that out yet. Well, we saw that the man in our sim had to pull on the gas out to the left, but in reality the gas is under pressure, so all the guy would have to do is just let up a little bit and the gas would push on him. And if the gas is pushing on this wall by itself and expanding into that space, the gas is doing work on the man. So if the gas is doing work, it should be losing energy. We'd have to add heat to maintain its pressure and its temperature. So if the gas expands, the work done is negative. So going back to our table, we fill in a negative value for the work done. All right, B to C, let's go back. We know that the work done is 0, but what about the internal energy? Well, we see PV started at 80,000 joules, and it dropped. I haven't actually calculated it at C yet. I'll do it in blue so we can see it here. P times V, pressure is 2 kilopascals, so 2,000 pascals times 10, so it drops to 20,000 joules. P times V at location C is 20,000 joules. So if PV is dropping, then so is your temperature. So from B to C, delta U is negative. It's losing internal energy. Now if you look at our ideal gas law, if delta U is negative, let's just write it out on the table. Delta U equals Q plus W. We see that W is actually 0. Delta U is negative, so it stands to reason that Q would be negative. So for this little box here, heat would have to be removed. So I'm going to erase the clutter there, and we'll see how that looks on our simulation. So Q for that little region will be negative. So let's check that out in our sim. Okay, so once again, from B to C, PV drops from 80,000 to 20,000. So because PV is related to temperature, the temperature must drop, but the volume must stay constant. So if I open up my simulation, how can we get this temperature to drop while doing nothing to the volume? Well, all I'd have to do is remove heat. So I put it in an ice bath, and we see that my temperature drops quite substantially. Now, lastly, we go from C to A. Now, C to A represents a volume change of 10 meters cubed down to 6 meters cubed. So we're squeezing the gas. And if we make the gas smaller, according to our simulation, this guy will have to push to the right. So he's doing work on the gas. So we know the work done is going to be positive. So let's fill that in first. Okay, so work done is positive from C to A. We've got that value. Now the pressure remains constant. So let's do the simulation and see what actually happens, and then figure out what we have to do to keep the pressure from changing. So it's an isobaric process, which means constant pressure. So we already know that we have to do work on the gas by squeezing it. Let's watch our pressure gauge over here. I start to squeeze the gas, the temperature goes up, and the pressure goes up. But I don't want the pressure to go up. So what do I have to do? I've got to remove heat. So Q has to be negative for this process until I get the pressure all the way back down to where it was originally. So Q is negative. Let's fill that in. Lastly, we've got our change in internal energy from C down to A. We know that our work is positive because we're squeezing the gas. We know Q must be negative, but what happens overall to our internal energy? Well, if you look at this process, and we saw what happened, we had to remove heat. What happened? The temperature also dropped in our simulation, and you can see that PV at location C is 20,000 joules, and PV at location A is only 12,000 joules. And once again, since PV is related to our temperature, then we know that our change in internal energy must be negative. It's losing internal energy as it goes back to A. So our last one is negative as well.